So here's a little quick review on graphing with square roots and cube roots. Also, this could be applied to general radical functions as well if you knew the parent functions. So what we're going to do first here is graph a square root. Notice I can tell that it's a square root if I zoom in here on the actual function itself and see that that is a square root because the index is not present. Or I can just kind of look at it without zooming in and say, hey, that's 2 times the square root of x plus 4 minus 1. So for a square root, a basic square root of x parent function always contains the following points: 0, 0, 1, 1, 4, 2, 9, 3. Remember, because when we take the square root of x, we get our y value. So the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. And again, we're looking at a square root function, so we are just doing the top half. We are not doing plus or minus the square root. So all of our graphs for square roots start at those points. Remember, I told you in class that you can actually plot those points first if you would like to. Just don't draw them very darkly. Be prepared to erase them after you use the 2 and the 4 and the 1 also as you change your parent function. So first of all, let's talk about what does the 2 do. The 2, remember, multiplies the y values. Because it is in front of the square root, okay, it is multiplying the y values of the function. Because if you take the square root of x and then you multiply it by 2, it's going to multiply these y values. So it does not affect the x values. Basically what it does physically with the graph is it either stretches it or compresses it, and sometimes it can also flip the function. So in this case, it is a positive 2 times the y values. So what you do is you come over here to the points that you just graphed, the original square root points, and you multiply the y values by 2. So what is the y value here? It is 0. 0 times 2 is still 0. This point right here will never, ever stretch, compress, or flip. So the 2 out in front will never affect this. Even if it was 10 million out in front, it would still stay at 0. So then what's the y value here? 1. What is 1 times 2? That is 2. So this point stretches up to 2. You can erase the old point after you stretch it up to 2. What's the y value here? 2. What is 2 times 2? 4. So it stretches that point up to 4. Notice it is not moving it, it is stretching it. That is important to understand. What's the y value here? 3. What is 3 times 2? 6. So it stretches it up to 6. So notice that if we were to connect these points, you would see a graph that looks exactly like the first one that we did, but it has been stretched out. It has doubled in size vertically. So it stretches out twice as big. If it was a bigger number, it'd stretch farther. If it was a smaller number, like a fraction, it would actually compress the graph down. If there was a negative 2 out in front, it would flip these down below the axis, and it would change our graph to be going downward. But it still just multiplies the y values. Finally, what we check for is we check for what does this number and what does this number do. So remember in class I gave you the technique of looking at those two numbers as opposite and same. That is an oversimplification of the process, but I'm trying to keep it as easy as I can on you. What you are really doing is that you are shifting your graph horizontally with this number and shifting your graph vertically with this number. The tricky part is this one is always the opposite. So this graph would actually move left 4 spaces. Even though it says plus 4, it's going to move left 4. Because you can actually plug in -4 into this and still get an answer Remember we talked about how you normally can't plug negatives into a square root, but you can on this one because the plus 4 cancels out the negative 4 to 0. This number always just subtracts from the total value or adds to the total value. So since this one subtracts, it is going to do the same thing we expect it to do. It's going to go down 1. So essentially, after you've multiplied all your y values and stretched it out twice as big, you just take every single one of these points right here and move them left 4 and down 1. So this one would move left 4 spaces and down 1. This one would move left 4 spaces and down 1. This one would move left 4 spaces and down 1. You could also erase these points as you do that, or if you want to leave them to compare and make sure you actually did it right, you can do that. Left 4 and down 1. The key thing is that at the end you know that those points, the red points we just erased, are not the final graph. The final graph starts here at negative 4 and then goes through my points this way. Remember with the square root, it always starts at that point and goes this way because you really can't plug in any of these negative numbers this way. Look at your domain as we talked about it in class. The domain of this function would be any number that is greater than or equal to negative 4, because you can plug in negative 4 now because of this plus 4, but you can't plug in anything like negative 5, negative 6, negative 7, negative 8, negative 9, you can't plug in any of those, but you can plug in negative 4 and everything this way. So your domain starts here and goes this way. So that is the numbers that I can plug in for x. Remember also on the square root graphs we did talk about the range as well. Notice the range is any number greater than or equal to negative 1, because your graph starts at negative 1 and goes up. Your graph begins here at negative 1 and goes up. So that also is noticeable if you look at this graph moving down 1 space. That should make sense. Okay? Just be careful if there's a negative in front of this, it would flip it upside down, so it would change your range a little bit. So let's take a look at a cube root. The process behind finding the graph for a cube root is basically the same idea, except for your starting points, your parent function as we called it, are a little different. Remember we talked about those points being negative 8, negative 2, negative 1, negative 1, 0, 0, 1, 1, and 8, 2. Because you can actually plug in a negative inside a cube root. The cube root of negative 8 is negative 2, because negative 2 times negative 2 times negative 2 is negative 8. So you can actually take the cube root of these numbers, including the negatives. So your graph for a cube root starts at negative 8, negative 2, negative 1, negative 1, 0, 0, 1, 1, and 8, 2. It kind of has that flat looking S shape to it, like we call it. When you are going through and graphing this one, you start it the same way that you do with a square root. You take this number that's out in front and you multiply the y values. So you multiply the y values times negative 4. So notice what the negative 4 is going to do. It is going to take this graph and it is going to multiply it by negative, so it's going to flip the graph, and it's going to be 4, so it's going to stretch this thing out pretty large. The y value here is negative 2. What is negative 2 times negative 4? Positive 8. Notice it flips it and stretches it way up. I'm going to show you what that looks like, and I'm going to leave the blue points for right now. What is the y value here? Negative 1. What is negative 1 times negative 4? Positive 4. Flips it, stretches it. 0, 0, what's the y value? 0. 0 times negative 4 is still 0. This one does not flip or stretch or compress. We talked about that with the square root. It works the same way with the cube root. The y value here is 1. 1 times negative 4 is negative 4. Flips it, stretches it. And then finally this point, 2 times negative 4 is going to be -8. Flips it, stretches it. So notice that this graph here curves through here, large looking S shape, upside down now, because the 4 flipped it and stretched it, the -4, excuse me. So the original was a flat looking S. The red graph now is flipped and stretched by a factor of 4. So now I'm going to erase my blue points here, get those out of the way because we flipped it and stretched it here. Now we're going to take the 2 and the other 2 and do the same thing we did with the last problem. Opposite, same. So we're going to move this graph to the right 2 spaces and up 2 spaces. So we go right 2 and up 2, right 2, up 2, right 2, up 2, right 2, up 2, right 2, up 2. So you can see that that graph is still the same shape, still the same curve, but has been moved right 2 and up 2. My final task is to just connect the dots. Remember, Mr. Harrison's not going to be judgy when it comes to how well you connect the dots because of my inability at times to draw very well with this bamboo tablet. So you connect the dots and you've got your final graph. So that's a quick little review of graphing square roots and cube roots. You need to memorize those parent function points, multiply the y values by the number in front to stretch it or compress it or flip it, and then you need to move it opposite same with the numbers that are inside the radical and out, adding and subtracting.